We did the Green's theorem, which is if you integrate counterclockwise around the domain, the same as integrating the two-dimensional curl over the entire domain. That's the curl form of the Green's theorem. Usually the Green's theorem means this one when they just say Green's theorem. The three-dimensional analog is like the following. Suppose, think about something like a gentle roller coaster ride. Think about it like this, but something that doesn't have like this thing. Something that's gentle, like toys roller coaster. Now, in 3 dimensions, if you think about a closed curve, the closed curve might not be enclosing a flat surface. It could have something like this. So imagine that you have a curve enclosing some bent surface, something like a potato chip. Right? So it's like bent. In this case, a theorem similar to this can be written for surfaces in 3 dimensions. But for me to explain that, I first have to explain this thing called three-dimensional curl. So if you have L, M, N, if you have a 3-dimensional vector field, the curl of a 3-dimensional vector field is I, J, K, round X, round Y, round Z. That's how we compute the curl, right? Notice that this actually gives you something I, something J, which is a vector value thing. Okay? So the curl in 3 dimensions is a vector value thing. That's because in 3 dimensions, when you have a vector field that's like rotating, you have to ask, you have to pick an axis of rotation to talk about the rotation. So what it does is, I explained that curl really talks about the rotation of the vector field at a point, right? But in 3 dimensions, if vector field is doing something strange around this one point, and if you wanted to know the rotation around a certain thing, you first have to choose an axis. So let's say this is the axis that you have. Then if you choose this axis, you pick a unit vector u, and only when you dot the unit vector u with the curl of the vector field, you can figure out the rotation of the vector field at this point going around that axis. That's how this curl thing works in 3 dimensions. Okay? So once you know that, then what you do is you do something similar. You cut this into many small pieces, and at each small point, you talk about the curl is some vector field, and then you choose this upward normal vector. So n is now an upward unit normal vector. Okay. And if you take the curl and dot it with the upward unit normal, you get the rotation of the vector field around this small point. And then if you add them up, first multiply by ds to get the rotation around this small square, because that's the density of the rotation. You just multiply by the area, you get the entire thing. Notice that I'm using ds rather than dA. That's because my area is not flat, it's a surface. So in that case, people use ds. Okay? And then if you integrate this over the entire surface S, that's same as the integral of the vector field F going around the boundary of S counterclockwise. And this theorem is called the Stokes theorem. And in most cases, instead of writing it this way, people just think about ds times n vector as this being the magnitude and this being the direction, and think about a ds vector. So often the form of the Stokes theorem that you're going to see is going around the boundary f dot dr, that's equal to, over the surface, you integrate curl, which is usually calculated as nabla cross f, dotted with ds vector. This is capital S. Okay? That's the Stokes theorem that people write down. Okay? On the other hand, there is also the divergence form of the Green's theorem, right? So what's the divergence form of the Green's theorem? It's if you have some boundary of D, you take f dot dn, dot n, where n is the outward normal, and you integrate, and that gives you divergence of f dA over the entire domain D. And then this side was a flux. So in 3 dimensions, flux takes the following form. Instead of having a domain or surface, it's a 3-dimensional region that you have in 3D. And flux is defined as if you have a region. So the 3-dimensional analog is if you have a region in 3D, let's say some domain in 3D, the boundary of the domain is no longer a curve. What is it? The boundary of the domain is a surface, right? So you have to do a double integral, not a single integral. And if you do f dot n ds, right, that calculates the flux of the vector field going through this region D. And that's equal to triple integral over the entire domain D of the divergence of f dv. So this one's called the Stokes theorem. This one's called the Gauss Divergence theorem. Now you're going to see this a lot in electromagnetics and fluid dynamics. Let me give you some examples. Okay, so you learned in physics 2 that flux of the vector field, electric field. So here's the electric field. Right? Flux of the electric field over some domain D has to do with the total amount of charge enclosed. Okay, actually, this is charge enclosed over the electric permeability, right? Vacuum permeability of the permeability of the vacuum. Okay, so that's what you learned in physics 2. Now, if you write this in an integral form, this is how you write it. This is how you calculate the flux, right? So in order to calculate the flux of this domain D, you do a double integral of E dot n ds equal to Q over E, but usually instead of Q, people write down 1 over epsilon naught of triple integral of the charge density rho dV on the boundary. So this is something that you learned as one of the Maxwell's laws. Okay? If you recall that there's a Maxwell's law, and this is the way people write it. However, if you rewrite this side using this, then this is what you get. You say that, oh, this is a triple integral of divergence of E dV over D, and this is equal to that. Therefore, this single integral formula can be written as a derivative formula which says divergence of the E is charge density divided by epsilon naught. So Maxwell's formula has 2 types of forms, one an integral form and one derivative form. And more advanced textbooks will be using this, but it's same as this one. The only way that you can know that the two sides mean the same thing is when you understand the Gauss Divergence theorem. Okay. That's why it's so important. Yes?
Is the divergence theorem for like closed surfaces?
Yeah, again, it's only for closed surfaces. Just like when this one is only for closed curves, this is only for closed surfaces.
So
Yes.
stroke is curved surfaces.
No, this one is it's a surface with a boundary. Stokes theorem is a surface with a boundary where this is a closed curve.
Okay.
Yeah. So that is this is a closed surface. It encloses a domain. This is it's a surface whose boundary is around this.
So green is only 2D.
Green's theorem is only 2D, and they have counterparts in 3D. One is called Stokes theorem, another is Gauss divergence theorem. So hopefully this was enlightening.